Hello, my name is Viktor Kopyev. I'm working in Central Aerohydrodynamic Institute, and our institute deals with any problems of aircraft. My lecture connected with the Kelvin Helmholtz instability and some questions which are connected with this remarkable problem in fluid instability. And a few words about aeroacoustic. And then I think you understand why this problem is so closely connected with the Kelvin-Helmholtz instability, with instability waves, and the problem of turbulence. Aeroacoustics is the problem of the noise of civil aircrafts. And perhaps you know that there is a ICAO rules which strongly prohibited for the noisy aircraft to be involved in the not only in market but in the using, and therefore for the landing in the airport of different countries. If the aircraft is so noisy, it is impossible to exploit this technique. And however, the aeroacoustic is strongly connected with the problem of turbulence. Why? Aeroacoustics is a area of science which are between classical acoustics and classical aerodynamics. For example, classical acoustic problem, the noise from the sound driver. And there is a vibrating membrane, and this is vibration produced the boundary condition for the ordinary wave equation, and therefore we immediately obtain the solution for the sound waves. However, there are no any rigid surface, no vibrations, and we have a usual flow. For example, you can imagine you drive in the car and put your hand in the window, and you immediately listen the noise which connected with the separation from your hand. And this is the unsteady properties, unsteady boundary conditions produced by turbulence. And no any rigid surface, no any vibrations. Nevertheless, the noise exists, and this is a very important industry problem. However, it is this problem have very deep problem, scientific problem. And what is the turbulence? We not have a discussion of the turbulence so many. We only few words about this remarkable phenomena, and it is clear that turbulence connected with the instability of flow. It is well known, perhaps not so well known, but it is in lectures. Not only me, but my colleagues often say that the unique problem which was formulated in 19th century, scientific problem, and have not solved in 20th century, is the problem of the turbulence. And even more, in the remarkable report of John Lamley, he noted that Richard Feynman, it is a famous physicist of our century and 20th century. I believe you know the Feynman lectures, series of lectures, and he said that, as if it's he said, I not listen, and it is only the remark of John Lamley that Richard Feynman called the problem of turbulence as the last great unsolved problem of classical physics. Therefore, the turbulence is from this point of view, we are in the center of the real science. And I believe it is very important for your community who deal with, you begin to deal with the science. And now about Kelvin Helmholtz instability. It is one of the possible instability. It is well-known instability. And then later we will discuss about this phenomena, and I will try to explain you how it appears, and why this instability could be connected with the problem of aeroacoustics. Now, some example of the turbulence in any aircraft details and in aircraft elements. This is a sled, and this is a turbulence from the numerical simulation. Quite nice picture, and this is a turbulence when the landing gear leg streamlining by the flow. We also have a separation which looks like that the hand in the window of the car, which I have already noted. And this flow, and now this is a jet, and later we mainly will be in mind exactly this flow. And this flow is a classical turbulent flow, and no any rigid surfaces, and there is a turbulence, moving turbulence, which produced the disturbances, and it is very difficult problem to formulate the noise generation theory, and it was started on the middle of the last century, and it is not finalized to the moment, and there is many open questions. Even in this, it seems most simplest problem of the turbulent jet noise. And now many questions and many problems trying to decide with the numerical simulation. Time to time it is a good approach, but not everything, because the numerical simulation usually it is a experiment on the table for the scientists, and however only the theory, only the idea why this phenomena appears and how to control this effect, it is mainly the problem not for the artificial intellect, it is not for the computer, it is for the scientists. And now it is also some example of the Kelvin Helmholtz instability in the internet, and very nice picture, even the in the art. It is a starring night, and therefore from the Van Gogh, and this is a numerical simulation for the specific situation where there are two flow symmetry half plane. In the bottom there is a flow on one side, and the upper half plane with the flow in the different side, and we mainly will consider the same situation in the other reference system. When the load half plane there exists the steady flow u0, u sub 0, and on the y larger than 0, we have no flow. This is a classical situation with the vortex shear, and this is the jump of the velocity, or it is a discontinuity of the flow. It is different explanation, one and the same. And this problem is the starting point for the Kelvin Helmholtz instability, where there is a jump of the velocity. And consider the picture, right picture, and suggest that there is a small hump on the surface of this vortex sheet. And we can remember, use, or to see in the handbook the Bernoulli equation. And according to Bernoulli equation, there is a constant, the following combination, which is drawn on the slide. And we see that on the under the hump, where the flow have the such current lines, and the cross section of the flow is larger than before the hump. The velocity must decrease because the flow flux is constant. Nevertheless, because the size, the cross section larger, and therefore the velocity must be decreased, and therefore, according to Bernoulli equation, we see that the pressure must increase because the total could be the constant, and therefore under the hump the pressure increased. Therefore, we immediately obtain on the next moment that the hump will increase, and this is some qualitative consideration of this phenomena. Any hump, any disturbance will increase accordingly the hydrodynamic properties of the fluid. And now consider the quantitatively this problem, and it is necessary to consider some easy formulas. Nevertheless, it is necessary. First, we consider the so-called Euler system of equations. The first is the continuity equation, well known in many problems of physics. It appears, and in hydrodynamic it appears, and accordingly the following very easy consideration. Let we have 1D, one-dimensional flow, and we select some small volume, some disk, and it is on the picture. And what is the balance of mass for this element of fluid? It is easy to write the mass balance and the difference of mass for this element connected with the difference of the mass flux in flow and outflow from this for two cross section first and bottom, and therefore we immediately obtain the formulas in the middle of the slide, and now if we consider and we go to the very small disturbances, we immediately obtain 1D continuity equation. And for 2D, it is in the red frame on the next, and now we consider as the simplest situation the incompressible fluid. It means that the density is a constant, and therefore we immediately obtain that in 1D situation du over dx x is equal to 0, and the same for the 2D, and this is the same as the 3D. It means that divergence of the velocity is equal to 0. And next equation, it is a momentum equation, or it is a second law of Newton, and we also select some volume and consider the balance for the momentum for this element, and delta p squared is a difference of the momentum for this element, and what is the reason for difference of the momentum? It is a flux of the momentum in flow and outflow, and also the pressure. Pressure acts as a force, and then we draw the second Newton's law and obtain momentum equation, the second equation for the in the system of Euler system of equations. If we consider the compressible situation, we are to add some equation for the connection between pressure and density, but now we consider the incompressible flow with density is equal constant. And now we see that the problem which we are trying to resolve, we're trying to explain, to describe the disturbances in this situation. To the left in the blue frame and in the blue phone, we see the equations for this system where for y less than 0 we have u sub 0 in the equation, and on the y larger than 0 we have the simplest equation, and you see, because no mean flow. Yeah, and now suggests that there is a potential of flow. I will not explain when the potential exists. It is a exists in vorticity and so called, and therefore let's potential exist, and it means that velocity is equal could be described as the derivatives of the potential, and therefore u disturbance of velocity is the d phi over dx, and v velocity disturbance is equal to d phi over dy. And when we substitute these formulas into the system of Euler equation, we immediately obtain that this system, and therefore it is a potential equation for the potential and in all part of the flow in the upper and lower half plane, and for the pressure in the for the flow under the hump, under the vortex sheet, we obtain the simplest equation, and when we have under the vortex sheet, we obtain a little bit complicated. Therefore, the pressure directly connected with the potential, because when we remove the d over dx or d over dy, we immediately remove the same in the right hand side of the initial governing equation and obtain this system. Okay, and therefore consider once more the picture and draw some disturbances, and now we have obtained the equation for the upper half plane and lower half plane. This equation, it is necessary to resolve. However, it is not enough. We are to connect the disturbances between these two areas, and this is so-called the boundary conditions. And also we need to use the condition that the disturbance must not grow on the infinity. And therefore, the first is the equality of pressure. and we have already on the previous slide see that it is very easy to connect with the potential, and therefore we obtain the equation 1. And the second is a little bit more complicated, and I will not explain in so more detail, but it is easy to consider the equality of the displacement field. Displacement is the vortex sheet, and the condition from the upper half plane and lower half plane, we try to obtain the properties of these disturbances, and because there is a lower half plane mean velocity, it appears the second term. Therefore, it is a little bit more complicated. However, this is an equation which means that displacement field could be obtained in the upper disturbances or lower disturbances, and therefore, of course, they are to be one and the same. And now we have the boundary condition, and we try to find the solution as the exponent which are to the left under the picture, and with the unknown amplitude A of y and b of y. It is the amplitude of this solution are the disturbances which proportional exponent kx and omega t, and this is a we try to find the solution in this form. And then we substitute this solution into the equations on the upper and lower half planes, and obtain at least the following. This is the amplitude where we use that the disturbances not grow on the infinity. Therefore, for y larger than 0, we obtain minus k y. It is exponentially decreasing of the flow, and the same for the lower half plane, and we obtain the b amplitude. Therefore, in the blue frame, we obtain the solution. What form of the disturbances could exist on the upper half plane and lower half plane, and it is necessary to meet the boundary condition. And therefore, we substitute this solution into the boundary condition, and then we obtain two algebraic equations, and then dispersion equation, which are in the blue frame on the bottom of the slide. And this is a almost final mathematical consideration of this problem. We obtain the dispersion equation. Dispersion relation is possible to say, and it is not so important. And therefore, only this type of the disturbances could exist. And now there is two different situations. In one situation, this one, we consider that there is a disturbances of the sign kx on the surface, for example, in the initial moment, and then we consider what happens later. Therefore, we obtain the time history of these disturbances, which we have the imaginary part. And the other situation, we could consider the when the omega is real, therefore it is real disturbances in time, and therefore we obtain immediately the increasing along the x, and this is two situations which I have just say, and usually it is a more popular. We consider the k as real, and this is a disturbances sign type, and it is increased, and we have usual manifestation of the instability. And the second is the space growth disturbances, and where the frequency is real. And consider the first situation. And this is a dispersion equation, and we have to the left formula for the omega, and where we are to analyze this solution, and we see that this solution would be increase in amplitude due to the second part, imaginary part, in the frequency. This is some manifestation of this effect in numerical simulation. However, in the different reference system, where there is a two flow, one on the left, the other on the right, but in our reference system, we have only the flow on the lower half plane, and therefore these disturbances would move in the half of mean velocity u. Okay, and now consider the problems with this solution. And this problem is so-called is ill-posed problem in sense of Hadamard. Why? If we consider the K real, this shape of the vortex sheet, we see that when the wavelength decrease, the increment, the velocity of the increasing of the disturbances also increase. And when smaller and smaller, the increment larger and larger. Therefore, when we have very small disturbances, they will increase immediately. And therefore, this problem is impossible to consider. Because we have not considered the initial problem in such a situation. And what does it mean? Consider any disturbances, any hump on the surface of the vortex sheet. It is a sum of the couple of the harmonic in X, and of course there is a harmonic with very small length. And if we have an angle, the disturbances will not exist at the next moment. Therefore, this is a situation, as I said, is ill-posed. But what to do? Because it is the simplest and very interesting and very important problem. And what to do? And we are to consider system so-called bounded growth system. For there, it is possible to consider the surface tension, for example, between two fluids. But in our situation, it is quite natural approach. We are to have a thickness of the shear layer. And if there is a thickness of shear layer, the small disturbances at X, of course, the increment disappeared. And therefore, the formula which are in the blue frame on the left of the slide is correct only for the long length of the disturbances, and for these disturbances, this shear layer, thin shear layer, would be the same as the vortex sheet. However, for the small disturbances, we see that there is a shear layer, and we immediately obtain that the infinite increment disappeared. Good. However, it is only half of the problem. Now, consider the second situation where frequency is real. Therefore, it means that anybody disturb the vortex sheet, and it appears the disturbances developed downstream, and this disturbance would be increased in amplitude, of course, due to the formula which we see, and if we substitute in the formula for the phi in the left corner of the slide, we immediately obtain it. Okay, and now there is a two different situation which necessary to be in mind. There is a system, there is a difference between two instabilities, so-called absolute instability and convective type of instability. We only to touch a little that you know that this problem exists. And in absolute instability, any disturbances, of course, it will be moved. Nevertheless, it is increased so fast that in any point of the system, the disturbance will increase. The other is a convective instability, when the disturbance, of course, it is increased. However, it is moved so fast that in any point of the system, the disturbance will disappear. And only this type of instability is reasonable to consider, because the absolute instability, to tell the truth, it is impossible to produce, because it would immediately transform to the other state, and we are to investigate the other state. Therefore, but we would like this, therefore, only convective instability system is reasonable to consider. Therefore, we believe to check the type of instability for different systems. It is a very complicated problem, and we I even not explain how to do that for you. It is, if it would be interesting for you when you will study it in the university, I believe you touch this problem, because it is very interesting and very interesting difference. And therefore, we suggest that our shear layer, that our discontinuity is the system with the convective instability type first, and then we consider the situation where omega is real, and then it is a gross disturbances along x axis, and then after, because the shear layer, for example, if now we will see the jet, if you remember, the thickness increase when the jet developed, and therefore these disturbances will achieve the thick shear layer and will dump it. Therefore, it's this instability form so-called instability wave. It is the second part which we also considered, and the concept of instability wave in jets. And this is a Kelvin, the instability wave. We mean that in convectively unstable system, it is a manifestation of Kelvin Helmholtz instability, and when it is exponentially growth, and then in thin shear layer, and then it decay when the wave achieves the region with a thick shear layer. Therefore, we obtain the wave pocket, which is the not one harmonic, it is a couple of harmonic. Yes, and now therefore the instability wave in low speed jet, it is transformed into could transform to the vortex ring, because the increment is so high, the transportation velocity is small, and the instability wave and form the vortex rings in the jet. And if we have a low speed jet, the instability wave have the form of wavy type of form, and therefore what is very important, that instability wave could directly radiate sound, as we discussed with you on the on the beginning of this lecture. Okay, and now one slide about the qualitative explanation of this problem without any detail. We consider the half plane, the instability wave, and we suggest that there is an excitation of the shear layer in the trailing edge of this half plane. And the difference between the incompressible fluid only that we have, instead of Laplace equation, we have the so-called Helmholtz equation. It is a wave equation for the harmonic in time. And we also obtained the solution, and then on the blue frame we have the dispersion equation, which also give us the shape of the disturbance which could exist. And Kelvin Helmholtz instability is exactly the pole on the complex plane of the parameter alpha. Okay, and suggest that we would like to decrease the amplitude of instability wave. The mechanism of excitation of instability wave is unsteadiness near the trailing edge, and suggests that there is a other type of instability and other type of excitation of the trailing edge, which could be remove the instability wave initial amplitude, and suggest that let's these instability waves radiate sound. Let's jet noise is important. Therefore, the way how to suppress the jet noise, it could be one way, one possible way. We trying to kill the instability waves which could radiate noise. Yes, it is a very complicated problem. They are not so good radiators. However, for very high speed jet, it is really important. Yeah, and we are interested in physics, and we would like to first to be sure that instability wave exists. Second, we try to control, we try to decrease their amplitude, and now before to demonstrate a few experiments where it is the manifestation and the experimental evidence of these effects. A few words about wavy wall mechanism, that you understand how instability wave radiate noise. The upper picture, it is a picture of the wavy wall, wavy deformation of the wall, which moves along x with subsonic speed. We this problem consider on the one of the first slides. It is very easy to obtain immediately that it would be exponentially decrease disturbances. However, it is a picture second. If the velocity of this wavy is high speed and supersonic, we immediately obtain the Mach waves, and the larger velocity, the larger supersonic velocities, then the angle of this would be changed, and therefore the couple of the this wavy wall with different supersonic jet, supersonic velocity will form the noise of this couple of the disturbance. And this is a wave pocket. And wave pocket which moves with the velocity u sub x, and exactly this type of instability wave really forms in the jet and in a real situation. And this is not a harmonic, this is a couple of harmonic. And if the ux is low speed, we will have this situation. And this is a spectrum of this wave which really exists, and only small part of this spectra really have a supersonic velocity, and only exponential small part of this disturbance will radiate noise. However, the second picture, where the velocity ux is high, and even better, it is a supersonic, we all the spectrum is a supersonic, and we have the real noise of all this system. And therefore, it explains why instability wave could be important in high-speed jet, especially in supersonic jet, could radiate noise. Therefore, consider the instability wave which formed by the sound driver which working in the lower half plane. It is problem is easy to resolve in the first principle. It is not so complicated problem, and we obtain the instability wave directly as we see the blue line, and it corresponds to this pole in the spectrum. And if we act from the upper half plane, the Kelvin Helmholtz pole is the same, and therefore instability wave is the same. The other diffraction field would be the other. However, in the stability wave, it's connected only with this pole, it is the same. And our goal, trying together that they are to be in antiphase. And therefore, it is so easy to kill the instability wave as and if it is important for the noise of the aircraft and so on, and the other problem in industry and so on, it is very important method trying to kill the sound radiating disturbance. Okay, and we consider the 2D problem. The same could be in a 3D for the jet, and now it is an experiment. We have the jet, it is a central flow, and we have a concentrator around the jet, where we could organize the field which would be disturb the instability wave on the other type from the upper half plane, as in the previous slides. And this is experiment, and this is not a jet, this is exactly the concentrator. This is the jet is a blue, and therefore we have a jet, we have a concentrator, we have a sound driver, and then we it is a PIV system, it is method for the measurements, and we see that the disturbances of the Vy, and then if there is a sound driver inside the jet, we obtain this form of instability waves, and then if there is a sound driver from the concentrator, we have a stability wave such a type, and then if we use together, we could obtain the situation where the instability wave would be killed fully. And this is measurements by the other technique. And for the high-speed jet, it is we consider on the previous slide with a very low speed jet, it is more easy, and for high speed jet, the situation is the same. And we also have for the disturbances could be add one to other or could be disappeared, and therefore it is not fully disappeared, but nevertheless we really could decrease the amplitude of instability waves considerably. And this is a numerical simulation, and the movie on the left corner in the blue frame, it is a filtration of the full disturbances on the surface around the jet, and we see that it is have a shape, character shape of the instability waves. And this is an experiment for the measurements of the near field of the instability wave, the way they are really manifest itself, and therefore it also could be recognized when the different Mach number and up to high subsonic speed and so on. And now the question, is it important? We go back to the aeroacoustics. The engine is one of the noisy elements of the aircraft. And how to decrease the noise? And the way of the subsonic aviation leads to the such type of the engine. It is a so-called high bypass ratio engine, where the diameter of the engine is high, therefore the velocity decrease, and accordingly the law of Lighthill, the noise of the jet is proportional 8 power of the velocity. And therefore this way is much more effective. However, for the supersonic aircraft, it is impossible to use this way because we cannot use the engine with high bypass ratio. Because there are the aerodynamic problem. It is impossible to overcome the and to come to the supersonic. And therefore, for this situation, the manipulation and control of instability wave could be very, very important. And now there is a reincarnation of the interest to the supersonic aircrafts, civil aircrafts, and on the other hand, it must meet the ICAO rules for the subsonic aircraft, and therefore it must be also sealant. However, subsonic aircrafts will have a long history, and the evolution of the engine, it is a 10th yes. For supersonic, the history is very poor, and therefore to the moment the industry have no answer how to obtain these results. And one of the possible results, it is also physical background, which we have just touched in the previous slide. It is a control of the instability wave, and trying to do that, and we can instead of the sound driver use the plasma actuators. Therefore, we will distort the jet by plasma actuator to control the amplitude of the instability wave, and it means that we will control the noise from this point of view. And it was very interesting and a lot job, and we have a joint project together with our partners in the Europe project many years ago, and it was many different type of plasma actuators that and we try to select what is the best, what is the most effective for this problem. And really it was fine, and we have some answer and what actuator are most robust and most effective, and however it is a other history. And now to the final some words. It is the jet noise. And however, there is the other type of the noise sources for the modern aircraft, and each noise sources is necessary to control, and it is necessary to obtain, necessary to recognize the structure of turbulence, the structure of radiating part, at least the turbulent, and trying to suppress this part. And therefore, the problem of turbulence in aeroacoustic is central. And for example, we consider the turbulent jet, and we consider only on the left picture only the instability waves. However, there is a small-scale turbulence, how it radiates noise, how it controls to these sources. The other is the pairing of the vorticity in the shear layer, and at least only the separate noise vortex could be the noise sources, and it is also important how to control this noise. And if we consider the other, the streamlining of the landing gear or any other element of aircraft, and very important, the interaction of the jet with the trailing edge for the high lift device of the aircraft. It is a different type of turbulence, different type of sources, and for all these types it is necessary to recognize how it radiates noise and how to control it. And therefore, as I have already said in the last sentence, and the problem that lie along all this path is linked with the problem of turbulence. And the first slide once more, the note of Lumley and the note which we believe was said by Richard Feynman, that problem of turbulence is a last great unresolved problem of classical physics, and therefore it is very interesting coupling of the industry problem and classical physics problem as well. Thank you for your attention.